So to kind of take all these concepts and put it into kind of an application to kind of open up for the next slide, an insurance company is trying to estimate the average number of sick days that a full-time food service workers use per year. A pilot study found that the standard deviation to be 2.5 days. How large of a sample must be selected if the company wants to be 95% confident of getting the interval that contains the true mean with a maximum error of 1 day? So basically, this is basically asking, it must be the end of the week, kids. Basically what this is asking is we want to come up with what size of a sample do we need so that we can have our X bar and then go plus and minus 1 and be 95% confident that our interval contains the true mean. All right. So to play that game, we just take the error and set it equal to that error term right here, and all we have to do is solve for n. So doing a little bit of algebra, multiply over by n, divide by e, we get this line squaring both sides. We get this nice little formula right here. So this is our sample size computation formula that we will use so that we can have a livable amount of error that we would like to have so that our interval is nice and small, along with the appropriate amount of confidence that we could come up with our z-score right here. And again, sigma's fixed. There's nothing we can do about that. So going back to this exercise right here, and let me just, n equals z alpha over 2 sigma over e squared. So in this case, we're told that sigma is equal to 2.5. We want to be 95% confident. So with our 95% confidence, we know that z alpha over 2 is equal to 1.96 from the table that I gave you the last time. And the error that we want to live with is equal to 1. So plugging all of this, we have that n is equal to 1.96 times 2.5 divided by 1 squared. So I think that by my computation, I came up with 24.01 with some rounding. Does that sound about right? And then according to our author, we don't do 24.1 since we're doing sample size. Usually nice. We don't sample half of a subject. So according to the author, we always round up. So if there's ever a decimal, round up. So we would choose a sample size of 25. So now this says we just go out and collect some information from 25 workers. We can compute the mean and then plug in the x bar. We have sigma at 2.5. We have n at 25. So the idea is that when you're done, the width of that interval should be a length of 2 at the end of the day, hopefully. Yeah, you get 5. Yeah, there is that. There is that. All right, so let's take a look at this example. Assume that we want to estimate the mean IQ scores for the population of statistics professors. How many statistics professors must we randomly select for IQ test if we want to be 95% confident that the sample mean is within 2 IQ points? The standard deviation is 10. So again, the formula is n equals z alpha over 2 sigma over e squared. So plugging in the appropriate parameters. So for z alpha over 2, what are we going to plug in? Survey says 1.96 times sigma, which is 10 divided by e, which is 2, and then I have to square this. So at the end of the day, I come up with a sample size of 97. So let's try one without our familiar, yes. 1.96 is the z-score for a 95% confidence interval. So to, all right, well, I just wanted to make sure that it's either A on the table that I gave. Is that? Oh, okay. 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 You're welcome. So a coffee shop owner wants to find the 80% confidence interval for the true mean cost of an espresso. So how large of a sample would he need if he wants to be accurate within a dime? Assume the true standard deviation of the price of the espresso is 23 cents. So let's kind of do this one the way we've been doing this, and notice that we need to compute the sample size, and we're going to need z alpha over 2, sigma, and our error. Well, these two are already given, so we just need to come up with our z sub alpha over 2. So let's just recall that alpha is equal to 1 minus the confidence level. So this is 1 minus 0.80, which is equal to 0.2. So alpha over 2 is equal to 0.2 divided by 2, which is equal to 0.1. So now we have an option as to computing our z-score. So remember, under the standard normal table, this lower-tailed area and this upper-tailed area are both going to be 0.1. So we need to get this z alpha over 2. So either A, you can look it up in the table, or B, you can use that built-in inverse norm command. So if we're going to use this, what value goes in for this routine? 0.1. So this is going to equal to 1.28. Actually, the calculator will return back negative 1.28, but remember, we said we're not going to concern ourselves with the signs for this particular realm. So plugging everything in, 1.28 times sigma, which is 0.23, divided by 0.1, square it, and at the end of the day, if you want to double check me and make sure I'm correct, that would be nice.